Math 287, Quest to College. I'm Joe Vasta, and now we do differential equations. Section 1.1, 1.2, 1.3, we're going to cover with this PowerPoint. It's just going to be some terminology for differential equations. We call this the basics. So what is a differential equation? A differential equation is an equation involving one or more derivatives of an unknown function. And we'll look at some examples pretty soon. A linear nth order ODE. So what is that? Well, that's what it looks like. A sub n of x, that's like a function of x. It does not have any y's in it, so it could be like sine x. That notation right there, that's the nth derivative. And then we have another function of x here. That could be the square root of x, and then this is the n minus first derivative, and it goes all the way down to the first derivative times a function of x. And then, well, it goes a little further, a function of x times just y, which is really sometimes referred to as the 0th derivative, and this equals f of x. And so there is a differential equation. The unknown function in here is y. And so we're going to be solving for y. Now that does look pretty nasty. Let's go over some of these terms, like what is an ODE and an order and all that other stuff. Linear. The derivatives, we'll start off with y. We'll label that as a derivative, the 0th derivative. So y, y prime, y double prime, etc. occur to the first degree only. So we don't have y double prime to the 4th power. It's the first degree only, and not as products or arguments of other functions. So we don't see the square root of y prime, or we don't have y prime times y triple prime, etc. So that's what it means to be linear. Order. Order is the highest derivative. So this says linear, which we have right here. Nth order, the highest derivative in this case is the nth derivative. Now let's talk about what an ODE is. An ODE is an ordinary differential equation. Why do we call it that? Because it's the ordinary derivative of one or more dependent variables with respect to a single independent variable, and in this case it's x. Now, contrast that to something that we're not going to do in this class, which would be PDEs, partial differential equations, where you have partial derivative of one or more dependent variables with respect to two or more independent variables. And so you can go to the university and take more differential equations classes, and you shouldn't be surprised to see PDEs there. Okay, so we've covered what linear nth order ODE is. Let's talk about homogeneous. Now this is a word that we heard in linear algebra, and you'll see that it's kind of the same thing here. A homogeneous differential equation is where f of x equals 0. So we have an f of x over here. Sometimes we call this the driving function, and that equals 0. Non-homogeneous is when the driving function, or f of x, does not equal 0. The homogeneous differential equation has the trivial solution. So what is the trivial solution? Y equals 0. And we've seen that before. Trivial solution is, you know, the 0 vector, or 0, 0, 0, or whatever. And if you put y, if this was homogeneous, if that f was 0, and then y is 0, its derivatives would also be 0. So 0 equals 0, and this statement really is true. A homogeneous differential equation has the trivial solution, y equals 0. Nonlinear does not satisfy the above equation. So we have nonlinear differential equations, does not satisfy this equation here. So there are nonlinear. And in this chapter, chapter 1, we'll be looking at first order differential equations, both linear and nonlinear. So chapter 1 is first order. Let's move on to the next slide. The next slide, we'll do some examples now. Now this equation here is not a differential equation, but we go back in time to your algebra class, and maybe when you first were learning how to solve equations, they had questions like this. Is x equals 2, is that a solution to this equation? And how would you figure that out? Well, one way of doing this is to write out the left-hand side and put x equals 2 into the left-hand side. So the left-hand side gives me 2 squared plus 2, because on the left-hand side of this equation, it is x squared plus x. And what does that equal? It equals 4 plus 2, which is 6. The right-hand side of the equation is just the constant 6. So the left-hand side equals the right-hand side. The answer is yes. 2 is a solution to that equation. The reason I did that is I wanted you to compare it to differential equations. Is y equals k times sine 4x a solution to this differential equation? So here's a differential equation where instead of a number, this is a function. Is this function a solution? Well, what we want to do is plug this into the equation. Before we plug it into the equation, we must know what y double prime is. So we're going to take 2 derivatives of this. K, by the way, is just some constant. Okay, and we're just going to keep it as k. So when you take the derivative, you get y prime equals 4 times k cosine 4x. A little chain rule there. The second derivative is negative 16k sine 4x. So now we're ready to plug things into the left-hand side. We have the y double prime, we have the y, and so what does the left-hand side give me? Y double prime is the thing we just computed right here, and then we have plus 16y, and there's the y. That equals 0, so the left-hand side is 0, and guess what? The right-hand side is just a constant 0. Left-hand side equals the right-hand side. The answer is yes. This function here is a solution to this equation. So now we have to get used to the fact that we're going to be looking for functions that solve an equation instead of just numbers. So let's move on to the next problem. Solve y double prime equals 1 over x squared. So this is a differential equation. It's second order. It's linear. How would you solve this differential equation? Well, you would just zap both sides with the antiderivative gun, or the integral gun if you want to call it that. And so the antiderivative of y double prime is y prime plus a constant, and the antiderivative of 1 over x squared, well, you've got to write that as x to the negative 2 and do all that jazz. You would end up getting negative 1 over x plus a constant. So I'm just going to put all the constants on the right-hand side and put them all into one constant. So y prime is negative 1 over x plus, we'll call that constant c1. Now I'm trying to find a function that satisfies this differential equation. My function should be y equals something. So I've got to now zap both sides of this equation with the antiderivative gun. So the antiderivative of y prime is y, and the antiderivative of the right-hand side, well, negative 1 over x would give me negative ln, absolute value x. The antiderivative of c1 with respect to x, that's what we're doing, is c1x, and then we have another constant. So there it is. This solution is valid on the interval 0 to infinity. Okay, because notice, if x equals 0, it's undefined. So sometimes with differential equations, we will put the interval that they're valid on. Now, we could have also said this solution is valid on the interval from negative infinity to 0, not including 0. But usually for applications, this is the more common one. solution that we have boxed in green is called an explicit solution because it is solved for y. Sometimes when you cannot solve for y, that's called an implicit solution, and we'll see that in section 1.4. Our solution boxed in green is also called a general solution because it has constants. Now let's go ahead and do a follow-up question to this. So we'll put all the information from this problem in the next slide. Y double prime is 1 over x squared, and we found y prime, and I put it in red for a good reason, and then we found y. And so there is the general solution, also explicit because it's solved for y. Now we have this, solve the initial value problem. So they give you these initial values. Y of 1 is 8, y prime of 1 is 2. So let's see how we do this. We start off with the y prime of 1, and you'll see why. You'll see why. Y prime of 1 is 2. So what does that mean? That means x is 1 and y prime is 2. The reason I picked that is because I want to focus on this red equation. It only has one constant, whereas the green equation has two constants. So I'm going to try solving for the first constant, c1, by plugging x equals 1 and y prime equals 2 into that equation. When I do, I end up getting 2 equals negative 1 over 1 plus c1, and we can easily solve for c1. c1 equals 3. Now I'm going to go ahead and take this initial condition. Y of 1 is 8. I'll write it down right here. What does that mean? That means x is 1 and y is 8. I'm going to plug that into the green equation because it has a y and it has some x's in it. So what happens when we plug it in there? I end up getting 8 equals negative ln 1 plus 3. 3 actually is the value of c1 times 1. So ln 1 is 0, and then we subtract 3 on both sides. We end up getting c2 equals 5. So I can plug that c1 and c2 into this solution here that we got, this function. And what is that going to look like? It looks like this. Y equals negative ln absolute value x plus 3x plus 5. Now this solution is still an explicit solution. It's solved for y, but it's not a general solution anymore. So this right here is not general. This is called a particular solution. Why? Because it has no constants in it. So let's move on. We are actually almost done with this overview of differential equations. In chapter 1, we solve first order ordinary differential equations of this form. Y prime equals. Now, this is a two-variable function. If you have not taken calculus 3, it just means it's an expression that has x's and y's in it. That's what we're going to be solving. This class is called ODELA. Well, the ODE comes from this part, ordinary differential equations, and then the LA is linear algebra. This equation will sometimes be written like this, dy dx instead of a y prime. So just know that. Here's the part that you're going to like about this lecture. Skip the homework in 1-1, 1-2, 1-3. It's just busy work. You can do it if you want. But the place we want to focus on is 1.4. And you've probably already done 1.4 types of problems when you took calculus 2. In 1.4, we study separable equations. Your first order differential equation, see this guy up here? Remember, it's a two-variable function. It's separable if you can take this two-variable function and you can split it as a product of an expression that has x's times an expression that has y's. And so this is what we're going to really concentrate on first. So in chapter 1, hopefully you'll watch the video for 1.4, and that's where we'll start doing the homework. You guys have a good day, and I'll see you in the next video.